Friends, let us continue with the 13th lecture in module 1, where we are going to talk about the continuation of analysis of non-orthogonal structures. We already said that in case of non-orthogonal structures, that is members which are not intersecting at 90 degrees to each other, k I of the member derived based on the local axis x m y m is valid, but need to be transformed to the plane of reference axis x y. We will talk about how this transformation is going to happen. Let us consider two orthogonal set of axes. Let us say x 1 y 1 and x 2 y 2. Okay? Let us consider this. Say this is x 1 y 1, okay, and this is x 2 and y 2. You will basically observe that y 1 is anti-clockwise 90 degree to x 1, similarly y 2 is anti-clockwise 90 degree to x 2. So, we are maintaining that relationship between y 1 and x 1, be it x 1 y 1 axis or other reference axis x 2 y 2. Okay. They have a common point origin O. Okay. Let x 2 y 2 be rotated anti-clockwise by theta degrees. Let us say this is theta degree. Okay. Now, I want to find out the components of these respective in the other coordinate. So, let us say this is going to be V 1, I call this as V 1 bar, okay, and I call this component, that is this component, as V 2 bar. Let us say this is our V. Let us now mark V 1 and V 2 such that they are mapped, okay, as shown in the figure. One can resolve, okay, x 1 y 1 to x 2 y 2 axis. So, one can say that V 1 is going to be, that is this component is going to be V 1 bar cos theta plus V 2 bar. Similarly, V 2 can be said as V 2 bar cos theta, because this angle will also be theta, minus V 1 bar sin theta, because the component of V 1 bar will be opposite to V 2. So, I can now express this in a simple matrix form. V 1 V 2 can be said as cos theta sin theta minus sin theta and cos theta of V 1 bar V 2 bar. We can express this as V is some matrix T of V bar. So, now I say T matrix is called the transformation. Okay. Alternatively, I can also resolve x 2 y 2 to x 1 y 1 axis. So, by that logic I should now find out V 1 bar and V 2 bar, is it not, which will be V 1 cos theta minus V 2 sin theta, and V 2 bar will be V 2 cos theta plus V 1 sin theta, expressing this in a matrix form cos theta minus sin theta cos theta of V 1 V 2. So, I should say V bar is T transpose of V. Please see this matrix, with this matrix you will see that this is actually a transpose of T. Okay. The rows and columns are interchanged. So, now two expressions, expression 1 and expression 2, both are valid, okay, where the T matrix is actually equal to cos, sin, minus sin, cos, okay, where C stands for cos and S stands for sin. So, we have two relationships now, which is simply V is actually equal to the transformation matrix into V bar, or V bar is transformation matrix transpose into V, okay, where the transformation matrix is given by cos theta, sin theta, minus sin theta and cos theta, where theta is the angle between the two axes measured in a specific style. I will come to that point. What I want you to pay attention is some specific properties. Let us look at this figure. Whenever we are connecting V bar to V, we are saying T transpose. Whenever we are connecting V to V bar, we say T, okay. And further, V bars are x 1 y 1 and V's are x 2 y 2. So, for any member which is arbitrarily oriented, let us take I have a beam or I have a column member, I have a shaft member arbitrarily oriented, which is similar to or parallel to this. Okay. So, now this becomes my local axis x m and y m, and this becomes my reference axis x and y. So, with this argument, let us say this is my xy axis and this could be my xm ym axis, okay. And therefore, theta is inclination or rotation of xm with respect to x measured in an anti-clockwise manner, okay. That is very important. In the last lecture we already see and understood that how xm and ym are given for or marked for a given section or a member, okay. So, xm should be considered in such a manner that the length of the member should be on the positive side of xm, and ym is 90 degrees anti-clockwise to xm, is it not? We already know how to select xm and ym for a given member which is arbitrarily oriented with respect to the reference axis x and y, right. Let us now look at the specific property of this T matrix, which is a transformation matrix. We know T matrix is actually cos theta sin theta minus sin theta and cos theta. Let us try to find the inverse of this matrix, which will be 1 by cos square theta plus sin square theta of cos theta minus sin theta and cos theta, because this is now equal to 1, which will be as same as the transpose of this matrix, is it not? Change of rows and columns. So, T inverse is actually equal to T transpose, hence the transformation matrix is orthogonal, okay. Having said this, let us now talk about transformation of the end moments and reactions of an arbitrarily oriented beam with respect to a reference axis system. Let us mark a beam which is arbitrarily oriented. Let us also mark the degrees of freedom. Let us say this is inclined by an angle theta, okay. Let us mark these values. Let us now mark the degrees of freedom. Let us say this is, we know it is theta p, equivalent end moment is m p of the ith member, okay. And we know this is theta q, equivalent end moment is m q of the ith member, and this remains my xm and ym axis. Okay. Then let us mark the vertical reaction along y, which is Vr similar to delta r, and we also have here Vs similar to delta s of the ith member. Okay. Let us also mark the axial deformations, which will be h t of the ith member causing delta t, and this will be h of the ith member causing delta H. Please note that all the symbols used here does not have a bar on the top, it means they are local. Okay. This is similar to a fixed beam which is arbitrarily oriented. Let us now try to map this, with reference to the reference axis which is x y. Okay. Let us mark all of them back again here. So, this is going to be m p bar theta p, okay. I am using bar of the ith member, and this is going to be m q bar with theta q of the ith member. And now, this reaction along y will be parallel to y. This was parallel to y m, this is now parallel to y. Okay. This value is going to be V r bar delta r. Similarly, I mark it here. Okay. This is going to be V bar s delta s, and this reaction like this was parallel to x m. So, this will be parallel to x. So, this is going to be h bar t I delta t, and this is going to be h bar h I delta h. Okay. The difference between these two figures are the following: all degrees of freedom displacement translations are marked without a bar on the top, whereas there are bar in all. Here the degrees of freedom are marked along with x and y plane, here they are marked on x y plane, which is the reference axis. Okay. Now, I want to see how I can map this onto this, or the reference axis to the local axis. Let us do that. Okay. The m p and m p bar, m q and m q bar, whatever may be the angle of inclination has no difference. So, let us write down that. I should say m p bar, m q bar, v r bar, v s bar, h t bar and h h bar. So, all these are displacements along the reference axis. Okay. This is reference axis. This should be equal to some transformation matrix and connect this to the local axis. I can equally mark this is going to be simply m p, m q, v r, v s, h t and h h. There is no bar. Okay. Let us go back to this figure. M p bar is as same as m p. Okay. I should say 1, and there is no contribution from anything else. Similarly, m q and m q bar are exactly mapped. So, 0 1 0 0 0 0. Okay. Let us talk about V bar r. We just now did this transformation of transforming any two value of V 1 horizontal and vertical. So, we will use that logic now and say that V r bar will be actually equal to, you can write it here, I can write here. So, V r bar, okay, will be actually equal to V r cos theta, is it not, plus h t sin theta, is it not. If you want to find V s, that is the right hand side, that is the kth end, this is my jth end, this is my kth end, similarly the jth end and the kth end. okay, at the kth end, you know V s bar will be actually equal to V s cos theta and H H sin theta. So, one can write this similarly for the horizontal forces, then one can generate the matrix as you see here. So, it is going to be 0 0 cos theta 0 sin theta 0 and 0 0 0 cos theta sin theta. This will be 0 0 minus sin theta 0 cos theta 0 and this is 0 0 0 minus sin theta 0 cos theta. So, now I can say m bar is actually equal to T transpose of m of ith member. Okay. So, this matrix is actually the T transpose matrix. So, by transposing this once again I will get T.